So in the last video, this is where we left off, and we were discussing this whole concept of taking phosphorus tribromide or phosphorus trichloride and reacting it with an alcohol. We needed pyridine in order to prevent the acid buildup, but overall, folks, here's the take-home message. I have an alcohol, I react it with PBr3 or PCl3 with some pyridine as the solvent, and the OH group will go away, and that gets replaced with a Br or Cl. Now, we mentioned that this was not the only way that we could protonate an alcohol in a way and get rid of it, right? Turn this alcohol group into a leaving group and eliminate it, and then substitute it with something else. Okay, so what was the other option? Do you remember that option? I hope so, because that other option was called thionyl chloride. All right, so let's take a look at thionyl chloride. I told you thio. Well, thio was a very good indication that sulfur was going to be present into a molecule. So thionyl chloride is this SOCl2. And the way that this is structured is a S double bond O with a chlorine to the left and a chlorine to the right. That's typically how we represent thionyl chloride in organic. And we need to talk about reacting this thing with an alcohol. All right, so I'm getting a little happy with my pen. CH3OH plus thionyl chloride. And we're going to say, what does it give us? All right, well, here's the story. We still need pyridine in order for this reaction to work. Just like PBr3, PCl3, we still need pyridine in that solution. So I'm going to take this alcohol, I'm going to react it with thionyl chloride, and when I react it with thionyl chloride in the presence of pyridine to prevent the acid buildup, same as before, something's going to happen. All right, so what happens here? Well, let's look at overall general scheme first. No mechanism. What's the product? Typically the easiest. It's typically what people like the best. Well, this OCH3, bam, becomes ugly and leaves. And this thionyl chloride gives that molecule a chlorine to be placed onto that OH group. That's it, folks. That's really all PBr3 and PCl3 did. Wherever the alcohol group was, it took that alcohol group off and it replaced it with a halogen. And the thionyl chloride option is no different. So if you're looking at overall product and you just want to kind of cut to the meat and potatoes, this is what we do. This is the product from that reaction. Now, let's talk about mechanism. It's very common that we want to know how these things work because, other than anything, it gives us a good review to talk about polarity and charge distribution and, what atoms are electron greedy and which ones are not. So we never really want to turn our back to these. It always gives us a very good review anytime they happen. So let's take a look at these molecules. The alcohol group has a free set of electrons here and here. That oxygen carries 2 of them. I can go ahead and do them on this oxygen too. That oxygen has 2 bonds and 2 sets. The chlorine down here, well, this chlorine has 3 sets of electrons. That's what makes its formal charge to be 0. So 7 dots. 1, 2, 3, 4, 5, 6, and then 1 from the bond is 7. Chlorine has 7 valence. 7 minus 7 is 0. Formal charge. So we're going to react these 2 things together. How do we do that? Well, mechanism-wise, we start with our negative piece and we draw it toward the positive piece. So let's take a look at the sulfur. If I look at the sulfur is getting a tug of war between 3 electronegative atoms. They're also negative all the way around. Poor sulfur. Found himself in a 3-way relationship and can't keep up with all 3. Should have listened. Well, because of that, this sulfur is going to be slightly positive. Chlorine's going to be pulling, I want. Oxygen's going to be pulling, I want. And that other chlorine is going to be pulling, I want. Imagine yourself in that position. There's no way. No way. So normally what happens here is that this oxygen's negative, and this oxygen's going to go, ooh, I heard through the grapevine that you give everybody that they want. Hey, Mr. Moneybags or Mrs. Moneybags, why don't we make a relationship together? And that sulfur says, no, I can't do 4. I'm sorry. I can't do 4 of these. 3's enough. And then that oxygen is going to come in and say, okay, fine. You're going to have to choose. I'm coming in, and you're going to give me what I want. And you're in a relationship with 3 other people right now, and I know you're overextended, but you're going to have to make a decision. You're going to have to get rid of something because I'm here and I'm staying. And sulfur looks at that chlorine and says, okay, well, you're the ugliest, so you got to go. I found a new trophy husband or a new trophy wife. Well, that chlorine is going to end up leaving. Pop! Off it goes. So now what we've done is that we have made kind of an intermediate here. We're working ourselves through the mechanism. How does this process work? That's what we're doing. So now we have this CH3, and we have this oxygen. I'm just going to draw the hydrogen down below because I'm going to do something with that in just a second, and I want it easy accessible. So this OH, there's the alcohol group, and the O now has formed a new bond with the sulfur that's double bonded to an oxygen, and it still has one of those chlorines on it. It only got rid of one. That was it. Well, this oxygen's got a problem. This oxygen's found itself in a position now where it's got 3 bonds. It really only wants 2. That's the rules of organic. So we're going to have to get rid of something, and it looks at something that's easily disposable, and that's poor old little hydrogen. But we need something to come in, and we need something to pull that hydrogen off. Well, that's the purpose of my pyridine, just like before. All right, so here's pyridine, double, single, double, single, double. It's got some free sets of electrons on it. And this pyridine, because it's a solvent, there's tons of it. Statistically speaking, this is a base that's going to go in for the kill. So this base, there's my negative, there's my electrons, will point to that hydrogen. Pop, off it goes. And that O and the H get into an argument. And they say, hydrogen, you got to go. I'm tired of you. But when you do, I want you to leave everything that we bought together. And hydrogen says, fine, I don't need them. So those electrons go up to that electronegative oxygen. If the pyridine was not there, well, look at what we just did. In this previous step, chlorine was just popped off of there. And that chlorine is a base. That chlorine is a nucleophile. The chlorine could have went in and tackled the hydrogen and pulled it off. And that would form HCl, which is an acid. And now all of a sudden, folks, we're back to an acid and an alcohol reacting again. And the whole reason of using thionyl chloride is no rearrangement. But if we allow this HCl or HBr or whatever the case is to form in solution, that defeats the purpose because now we get a mixture of products. So the pyridine prevents this from happening. That way we can ensure that the rearrangement does not take place. All right, so we're not yet done. So now what we've ended up with is a much happier molecule, this CH3 with an oxygen that has on it a sulfur, double bond O, and a Cl. All right, well, this oxygen's finally happy, right? 2 bonds, 2 sets of electrons. Everything else is pretty happy as well. I mean, if I want to draw the dots in there, I can. I don't really have to, but they're there. Blah, blah, blah. They're there. But now what we do have is that chlorine that's still in solution, right? This was from the very first step that we did. So that chlorine is still swimming around. Still out there. We can't forget about it. So this chlorine, well, it's ugly. It's a very good leaving group because it's ugly. Again, all of that is based on nucleophilicity and bases. But you know what's uglier? That chlorosulfite group. That's what we call this, a chlorosulfite group. That chlorosulfite group is way, way, way uglier than that ugly chlorine. So if that carbon had to make a decision, that carbon's in a relationship with that oxygen, that chlorosulfite group, and just nothing's there. There's no sparks. Poor thing. I mean, they're trying to make it work, but nothing's going to happen. Carbon knows that. The oxygen-containing group knows that too. But, they're just kind of waiting around for someone to make the first move. So they go to the bar. And in comes an ugly old chlorine. And even though it's ugly, carbon looks at it and says, you know what? That's better than what I have now. So why not? So that negative chlorine is going to go into the carbon, and they're going to form a bond, and then this group is a very good leaving group because it is so ugly, uglier than chlorine, so it's a better leaving group than chlorine. And pop, off it goes. And now what we're left with is my CH3 that we started off in the very beginning, and a chlorine that's attached instead of the OH. All right, now let's take a look. Up here at the top, look at what we did. I gave you the overall scheme. I said, listen, when we add thionyl chloride, the OH goes off and one of these chlorines go on. And we said, there's your product. Do you see how easy that was? That should be how easy these reactions will be. But some people are not happy with that. I know. Blame them, not me. And that's why we go through the mechanism. Because we want to know, how does it happen? Right? I mean, does the OH just leave as an OH group? And does the Cl come in as just kind of a single, hello, here I am? How does that actually go forward? That's the purpose of the mechanism of the reaction. It's telling you how this happens. So as a general review, let's look. This OH group is attracted to the sulfur of the thionyl chloride, and that sulfur kicks off a chlorine. That begins to form this chlorosulfite group, which is a very good leaving group. And that chlorine that was out there, that was spit off in step number 1, comes back, and it says, wait a minute, I'm not done with you. And that chlorine attacks the carbon. The carbon and the chlorine make a new bond. That's our product. And that chlorosulfite group leaves as a very good leaving group. That's how this step happens. Now, let's do a little bit of summary, right? Because it seems like there's been a lot, and there has been. I mean, I'm going to be honest with you, there has been a lot. So if we take an alcohol and we react this with something like HBr, well, what happens? The alcohol leaves and Br goes on in its place. I'm not talking about mechanisms. I'm not talking about, bam, give it a black eye. I'm not talking about any of that. It's just the overall scheme, what goes on. Okay. Well, we can take another alcohol and we can react this with HCl, and the OH goes off and Cl goes on in its place. Look at there. That's not hard, is it? It shouldn't be. And again, we're forgetting about mechanisms. We're just wanting to write down products. That's all that we want to do. Now, in the chloride, keep in mind, the chloride is the prettiest of the halogens, and sometimes we might need a little bit of extra help. So, often they'll write zinc chloride up there at the top, and it's perfectly okay. That just is an extra oomph to get that off of there. Well, to tell you the truth, I mean, we're working with the halogen family. I told you that iodine is out there. It's a possibility, right? We stay away from fluorine, but iodine is out there, and iodine would really work the same way. We just really haven't done anything with it, but it's the same mechanism. OH goes off, I goes on. Now, what are the other options? Well, I can take an alcohol, and I can react this with PBr3. No mechanisms. What's the product? Well, the OH goes off, and a Br goes on in its place. Was it hard? No, it shouldn't be. And then I can take an alcohol, ROH, and PCl3, and folks, guess what? The OH goes off, and the chlorine goes on in its place. Look at there. And now we've talked about taking an alcohol, and this time reacting it with SOCl2, thionyl chloride. And what happens? The OH goes off, and a Cl goes on in its place. So when you begin to look at the number of reactions here, what you're going to see is that they all really are doing something very similar with each other. HBr, HCl, HI, OH goes off, halogen goes on. PBr3, PCl3, SOCl2, OH goes off, and the halogen goes on. That's the summary of what we've done so far. The difference between these. We're going to split this group in half. Down here, no rearrangement takes place. And up here, you do get rearrangement. So folks, there's a summary of everything that we've worked up to at this point. Now, the bottom halves, you need pyridine. In all of these arrows, I've left off the solvent, and that solvent is pyridine for every one of them, and it is used for the same reason every single time. It prevents the acid buildup. The acid buildups that we are worried with are right up here. We do not want these to get generated in the reaction, because if they do, then these reactions will take over and rearrangement will begin to happen. And the whole reason that we use these down here at the very bottom, the whole reason that we use them is to prevent the rearrangement from taking place. That's why. Okay? Okay, so that's where I'm going to stop this video. In the next video, we're not done with alcohol reactions. We're going to continue to go. And those alcohol reactions are going to keep adding up and adding up and adding up. That's just the way that it is, folks. That's how alcohol theory, that's how alcohol family just operates. There's so many different possibilities at this point that we can do in order to get that alcohol to be reactive. And we're not going to talk about all of them, but we're going to talk about quite a few of them. And it's going to be maybe hard at some points in time to keep them separate, but we'll walk through them little bit by little bit. We'll keep reviewing. We'll keep looking at these types of questions. We'll keep doing example problems. That way you will become more and more comfortable with the alcohol reactions. So what's up next? Well, what we're going to be talking about next is something called a sulfonate ester. All right, so bear with me. Make sure you got a clean sheet of paper out. It's a different type of reaction using different types of reagents with a different type of mechanism. Yeah, I know. Again, don't blame me. I'm just the messenger here. That's all I am. So I'll see you in the next video.